Okay, we should be back again for Advent of Code 2022, moving into day 15. Yesterday went better than previous days, which is promising, but we can still go faster. We have to crest this top 100 at least one more of these days this month. We've fallen down to 68, having not gotten any points for a little over a week. Still in the top 100, but again, personal goal is hopefully getting into 1000 at this point with so many days having passed. I think it's a little ambitious, but you never know. At this point, I would expect the virtual machine to come back. Like, my prediction this month is the VM question will come back maybe 1 or 2 more times. Maybe 1 more to develop the instruction set, and then another time adding a couple more instructions, and then some sort of optimization problem. That's just my prediction. I don't think it's definitely not another like VM heavy month or year, I guess, like the int code year, which is fine. But yeah, I have these files open just in case. They come in handy. But yeah, it might be, I don't know, yesterday was an interesting simulation question, so probably not like a automata question, probably like parsing and rules of some sort. Okay. Negative should be true. Seems good. Exists at integer coordinates. Each sensor knows its own position. The closest sensor. So none of the detected beacons seem to be. So you have to work out where it isn't. For now, keep thinking. Is this the closest on the same axis? No. Okay. So this is a sensor, and I think I'm wasting time with this, but I kind of just need to visualize. Okay, that's fine. The sensor detects a beacon. Consider sensor at 8.7, the sensor's beacon is 8.2. Sensor's closest is at 210. Oh, I see. Okay, so I guess it's... I think it's... You just kind of keep expanding out. So that's gonna be the furthest possible spot. The sensor is supposed to be between 10 to no beacons that are closer. So it like blocks out everything in that range, I guess. There probably is a better way to do this. So it's the closest, so there can't be anything. It's equivalent, so if from the sensor dot dist Manhattan is less than or equal to P is less than or equal to the dist, then maybe we would do it this way. I feel like this is wrong. Oh, we have to go out more, right? It's gonna be the distance between it, we have to go out the other direction. So... it's gonna be this minus distance, and then out to the furthest point, plus the distance. 17 is wrong, so kinda do want to see what this board looks like though. If we only simulate it for sensor, and then we want to print that, and let's only do this. Let's just see if this logic works correctly. Yeah, we're not considering a big enough range. We need to go... oh, here. Is that right? have to go, honestly. Okay, that seems better. 27, okay, and then what do we want actually? We want line 3, 4, 5, 6. Oh, I guess this isn't gonna work, is it? There are too many spots to fill in. So I guess we have to be a bit more clever about it. We just have to, oh, well we would do the opposite where we just check all the values in the range and see if they fall within these rules, right? So it couldn't possibly extend out further than how many people are smarter at geometry than me? Oh, a lot of people. Wow, it's only first star solves. That's kind of surprising. So this is an accurate simulation, I think, which is good. Oh, this shouldn't be in here. Still not fast enough to simulate though, so we do, I think, want to count the number of positions. So it's probably it's like the inverse problem, right? You just iterate through the positions in the rows and see for any of So we'll do 1, 2, 3, 4, and then for the test we do this, and then it'll be like do like the inverse problem, right? So for x in range, so it'll be I feel like this is super inefficient, but at the same time, people are struggling with part 2, so I'm actually really excited to see what it ends up being. But this will be a fun one to even get to that point, I think. Alright. So it'll be max min x minus max delta minus 2 max x plus max delta plus 2. P equals point of x target, and then we basically do this check. Oh, why did the song change? I like that Donkey Kong Country song. And then, so we have to check each of them, and if in all of them, what is actually the condition? If there can't be a beacon, oh, I guess we find the closest, oh, it's just, what, find the closest sensor to it, and then see if it's closer than the closest beacon to, oh, okay. So the closest is going to be none, and then also the closest distance is going to be so if p dot dist Manhattan to the sensor is less than CLD, then CL becomes the sensor. Okay, this is an interesting problem. CL becomes sensor. I don't know why it's like all the screen tearing going on is kind of annoying. So now we have our closest thing, and then we basically just ask if the distance from P to, what is it, to the sensor is less than or equal to the distance from, oh yeah, I think we actually just want the index, right? Sensors I dot dist Manhattan to the beacons of I. And then we just don't simulate anything. Got 30. Oh, okay, well I guess a beacon shouldn't exist. Are we checking too many points, maybe? How are people so fast at this? I'm definitely overcomplicating it somehow. Okay, we missed one. I mean, I guess there could, like, conceivably... You know, there are no other beacons that are closer. Maybe I'm just supposed to go through this for everything. Otherwise we overestimate. knows? So if it's... We want to find any position where it cannot exist. And I think currently we're like overcounting. So if the distance from the current point to the sensor is smaller, it definitely cannot be the case. So we break. Okay, that's promising. Why is there still so many checks? What does the input actually look like here? Still too slow. Why is that? I guess if we're only checking things in a given row, what, like, I don't even know what optimization we can make on this. What is better than just simulating? These numbers are only in the millions, right?
Been working at this lame factory.
Wait, where am I even?
Years.
Oh, I'm still running this code.
Give me some of that chaos control, man. Show 'em how it's done, House. Oh yeah. Let's do it.
Okay, I don't want to print you.
Let's go. Yeah. Come on.
Okay, wow, people are fast. The distress.
We
But the
ain't
distress.
playing around. No, sir. Oh yeah. Give me an Allen wrench. Give me a quarter wrench. We gon' work that sucker to death. Now, give me an Allen wrench. Give me a quarter wrench. We gon' work that sucker to death. Give me an Allen wrench. Quarter wrench. We gon' work that.
1, 2, 3, 4.
Give me a quarter wrench. We gon' work that sucker to death.
To isolate, you need to determine the frequency. So the search is smaller. So actually, in this case, it's 20. So, just for the sake of so I remember what we're dealing with. It's like, this is the spot, I guess, right? Let's just confirm that that's the case. Yeah, so it's like finding the little hole. So how do we... efficiently figure that out. The search space is so big, it's 4 million by 4 million, so we need to find a more efficient way of narrowing down what that spot is without actually doing the full simulation.
Give me an Allen wrench. Give me a quarter wrench. We gon' work that, work that. Give me an Allen wrench. Quarter wrench. We gon' work that sucker to death. Yo, give me an Allen wrench. Give me a quarter wrench. We gon' work that now. Come on. You have no idea how much I hated my job. Sir Jay and Mr. Halsey, Dr. Eckerman would like to see you in his office.
Okay, what's the trick here? Because I mean, is it possible to like split this and do the search in 2 dimensions independently? Maybe, because there's only going to be one empty spot in the middle, I guess. There's going to be one empty spot in the middle. What do we know about these numbers, I guess? It's like here we knew what the row was, and so we could guess at the location. Suppose we knew what the row was, we do a similar thing across where you just do a comparison on which things are filled in.
Now, listen, gentlemen. The reason why I called you here today is because basically...
Because, I mean, we can't do
you're fired.
4 million times 4 million different searches. How good are people? Oh, people are figuring it out, of course. I mean, my suspicion is it's going to be... Let's visualize this in a different way. Because my brain does not want to work right now, and the heck. So like A is closest to 1. This is our hole. Now the hole is hard to see. B is closest to... Hello? Do you want to give me numbers, please? No, I'm more confused than anything at this point. Where's my lowercase b beacon? C. This is not helpful. Like J is closest to J. So, what dictates like why does it feel like we're missing so many like, beacon locations? Oh, there's fewer beacons than. Oh, a lot of things are like closer. Oh, I see, I see, I see. Okay, well. I thought they were all unique. That's interesting. So this one's closest to this beacon. B is obviously closest to this beacon. Somehow there's a gap here. I feel like this is the problem that I'm not going to solve this month. But I will try at it for at least an hour. We have good music. Like, it's impossible to find by simulation, so we have to be a bit more clever about it. I guess we can sweep. What happens if we just like do a sweep and ask? Cause maybe it's like a local minimum type question? Like, question mark? If we do this sweep, and for every point, what do I want to do? For every point, we just pick an arbitrary xy and we pick the one that minimizes all of the Manhattan distances between the things and their closest neighbors, maybe? Maybe it's something like that. Let's not do this anymore. And let's map minimum distance. And let's do something like MD equals min of MD and what is this? PD? And then pos of x is equal to MD. And we'll see if this gives us anything good. I just kind of want the minimum distances, but like why are these numbers so big? Oh, I'm using the wrong target. Let's just fix that as something arbitrary. And let's make the like, do we get something useful out of... We're looking through possible x values. kind of looking for some sort of local minima or maxima around a given point. Was my hope, at least. Because the answer is going to be the point that is basically the furthest possible. Is it just the furthest possible point away from all the other beacons? Like, I don't think that that's strictly true either, but maybe it is. But I don't know how to optimize this in 2 dimensions. It's like, you could code up some sort of gradient descent, I guess, that tries to go in that direction. Oh. And what is the hope actually? We'll think about it for like 20 more minutes, and then perhaps give up. So we're trying to find this spot right here. I don't even know if this strictly is the point that's furthest from all the beacons. But maybe it is? Like, maybe it helps to reason through that. So, what do we want to minimize the sum of Manhattan distances? So maybe it's oh wait, no, I was saying it should be the sum of, right? I have no idea if this is even a reasonable metric or not. But okay. We want to sort by this and in reverse order. we're hoping to arrive at 1411. Which is this, so it doesn't exactly minimize it. Maybe we're supposed to do it's like I wanna it's like the sum squared distance almost, but I feel like that's not right. So maybe it's actually the thing that minimizes the distance between all the sensors? No, it still brings us to like 1111. I mean 1114 is like a pretty good candidate here. Oh wait, no, we want 1411, which is over here. And it should be the furthest thing away from... I mean, I guess that's not necessarily far away from the beacons or the sensors, right? It just has to, there's no beacon that's closer. For any given point, there's no beacon that's closer to it. So maybe you can just minimize the search space? No, it wouldn't have taken that many people that much time for part 2 to solve it if it was that simple. Is it really just like, you just narrow it down somehow with like a heuristic? So this like blocks off all this space just by virtue of it being... Is there an alternate representation of this coordinate grid that we can somehow use? Like, maybe the search space isn't actually this big. Maybe you can just peg it at somewhere central. Like, no. But you could make a clever input where these things don't necessarily overlap. I'm trying to figure out what the interesting property of this point is in relation to how the beacons and sensors are set up. I am surprised that we found the interesting thinky geometry problem on the 15th. It's like pretty early. I mean, I guess the interesting part about this point is that there are like I feel like we want to minimize the distance. Like as a rough heuristic, minimizing the distance between the sum squared of like all the sensors, right? Somehow, like I feel like that can't be a bad heuristic. Like maybe we do that to narrow. Oh no, but I guess we can't generate this list, right? We can't even generate this list to kind of narrow down some candidate spots. Because this takes too long to simulate. So it has to be something that can be done. Like two theories are you can do the search in two directions, axes independently from one another and combine the results. Or it has to be some property that you can infer from just the beacons and sensors alone without doing a full iteration over the search space in either direction. I don't think there's any other hints from the rest of the problem. Like it just so happens that we guessed and we scanned the correct row, right? It happened to be in y equals 11, but there's no way you can actually get that lucky. Like this is just arbitrary, there's no way it actually relates to this. So again, it leads me to think it's some property of but I guess there's no way you could. Okay, maybe we sweep. Right, you just sweep across. Let's just fix x to some stupid value that isn't correct, like 10. And we get 11. Now what if we fix y to some stupid value that's not correct, like 15? Oh. Okay, maybe let's and do that. Like we don't quite get or I think it's just coincidence. Maybe not. Like, no matter where we're searching the search space, we always come out with a y equals 11 minimizing the distance. We don't quite get close enough in this direction, but at least maybe we can spiral. We can use that as a starting point and like search out.
Amazing, astonishing, not bad.
Like how close do we get? We get like a decent number of initial candidates. Is it worth trying to code this up? Probably because I don't have a better way to do it. Do we get better if we use this distance metric? This is already squared. No, we don't. We get exactly the same. So I don't think this is the answer. Okay, so what's our logic so far? We try to sweep the entire search space for some candidate values in both directions. Sure, let's just try this out. So, and let's do this, and we'll just pick target in the middle. We'll just try to aim for the center of the board, right? That's probably a good metric. So for Y, in range, this is my best guess. So it's going to be point. We'll fix this at target is going to be X, and the Y is going to be here, and then for some squared error. And then distance is going to be the sensor, and then some squared error is plus equal to d times d. And then scene of the point is going to equal to t. And then we're going to sort. And we'll print the candidate like first 20 and see if this operates in a reasonable amount of time and converges. Ah, stop. That wasn't so bad. I mean, this is probably my last shot before I go to bed because I do have to wake up tomorrow. We only care about the point and we only care about the Y value, right? Because we're sweeping Y. This is dumb. This is just the start of the search space. There's no way this is actually minimizing anything. Oh wait, no, maybe it wasn't. How many digits is it? That should, for 6 digits we're good? 2, 3, 4, 5, 6, 7, oh we're not good. Do we not want to minimize ourselves? Yeah, okay. This was not a useful metric to go off of. I think it just coincidentally happened to work. Two 5998 842. Okay, yeah, it really is decreasing. So just decrease at the other end of the spectrum. Maybe if we decrease the search space a little bit from just the middle. See if we get some more useful numbers out of this. No, this just maxes out the range as well. Like otherwise the search space is way too big to just try everything with, right? I don't think it's possible. There's no way like the naive search is the correct way to do this. I want to solve this problem before going to bed. What is the tricky trick? What is the trick to finding this spot? It is a spot for which, over all sensors, there are no beacons closer than it. Yeah, so it's... Oh, so maybe you're supposed to maximize... No, there's no way the optimization problem is like a maximal. It's the furthest possible away from all sensors? That feels wrong. I feel like that's just objectively the wrong way to think about it. Like, it's minimized here. We do it this way. 14 is like there, but not at the top. I mean, we can just run this experiment again, I guess, over the full sweep if we're trying to like max. Like this. Yeah, this just gives values on that end of the spectrum, and if we do this, it's gonna get values on the other end of the search range, which is definitely not the case. It's like shouldn't be the answer at the very least. This one's a head scratcher. It's a head scratcher for sure. Like if you had a guess, you could guess where to pinpoint the search. You'd be good. But obviously, you don't have an oracle to figure out where that search location should be. Like, I also don't think it's as simple as the point that maximizes it's like just the point that maximizes the distance between all beacons? Beaks. Because on the edge of the search space, you're definitely maximally far from everything, right? It's like you only care about the internal points, almost. Oh, is it like... Voronoi. It's like... It feels like some reverse Voronoi problem. Where each of like these things that gets drawn, each of these diamonds that gets drawn, okay, maybe we'll break down the problem again. Each beacon, or each sensor, draws a diamond around itself. There's a hole in these overlapping diamonds somewhere. And you just have to find where it is. Oh, well... Like, how would you infer that there's a hole here? You know that there's like really big diamonds that cut off a lot of the search space? There's just too much to search through. It's... How do we figure it out? I said I would go to sleep, but figuring out this problem in one sitting without external assistance is gonna be the end of me. Okay, well, we know how to draw these diamonds. That's not the hard part, right? I guess the hard part is... Does the first part serve as a clue in the row where this is equal to this, how many positions cannot contain beacon? This is just a red herring for sure. Might give me a geometry bubble today. The harp holes are supposed to be on the weekends. It's gonna be some like... It's either gonna be really obvious or some crazy geometry overlapping volumes like proof stuff. You fix an arbitrary point. I guess... Again, what is special about 1114? Oh, it's gonna minimize the okay. Kinda just wanna... I think the location of the beacons doesn't actually matter. I want to compute a list of deltas, and deltas of this thing is going to be the distance from the B. And for any given point, we can compare the difference between how far it is from subtracting the does that even make sense? It's gonna be like one further than this guy. It's gonna be like one further than that metric. It's gonna be so minimizing that minus that. I don't know.
So help me break these chains. Now it's time to turn the page. Save me from the shadows. I put my trust in you. Come with me, my friends. This war I can't fight alone. Guide me where.
What is the math I'm trying to do? This is...
There's no turning back. We must face all our darkest dreams. I am so afraid.
So we find y equals... No, that's not right. This is bait, I feel.
But I'm not alone in this barren place. When all fades away, you stay by my side. And I was blind, but now I can see the future that lies just ahead of
Yeah.
me.
Just for good measure, whatever maximizing. These numbers are just close to the top of the range, right? 3, 3, 1 digits, 3, 3, 1. Could we have done 4 million times 4 million operations by now? What if we just leave this bad code running overnight? It's only a few trillion operations. PyPy will be able to crunch through that. It's an awful solution, but I might be calling it for the night. I mean, I guess that doesn't hurt to just have something else running in the background that's really naive, no? This is day 15. Call it bad. Like, what would the dumb code have been? This, right? This over the entire search space, basically. Six. This doesn't seem right. Great. Okay. Well, you know what we're doing. Bam. Where do we get stuck? Four, five, six. 1, 2, 3, 4, 5, 6. guess because we're actually like trying values in this range. Have fun. Maybe we'll get an answer. What is the trick? I mean, I do want more feedback that this is actually working. I did my mental math wrong. Like, what's going on? Why does it... What's happening? I'm just confused why this looks like it's freezing. On like the first, on like this final 1000. Like, are we getting stuck in some loop? Why do you just refuse to search anymore? I don't understand what part of the... Are these supposed to be continues? Can someone for X in range TM why the iteration is stopping here? This is a very confusing point to me. Why does it always stop here? What is so special about... It starts at 3999000 max. Is it? This is screaming parallelize me. I can't tell if it's like, I don't think it's a bug in the code, it's just... I guess if you were to draw this... Oh, I see. It's like all the action is happening over on, like, on this segment. It's where the fun stuff is going on. The sensor casts an absolutely massive diamond, right? Because it at least goes from this to negative about 7k. I just hope this isn't frozen. Wait, am I... Ugh, I'm not convert... Oh my god. Okay, this will be a lot better. Just straight off the bat. But we still kind of get to this point where I guess we don't have to check beacon if it's in the beacon because by virtue of us being Does this even do anything for us? Oh. So I mean, I don't think we need to check this case. I'm suspicious if this is even helping us, because I don't think it could possibly be overlapping a sensor spot. So I think this will speed up the search, but at the same time, it's like. This guy's chugging along. I think this is way too inefficient. Okay, well, we let this run. We think about how to be more clever. I also I wonder if this would happen if we were swapping our XYs. Like, why does it feel like we just... I mean, I guess it's just... Is it really just searching this many things? Yeah, okay, fine. I get it. It's slow. This is so slow. Like, this isn't gonna finish in any reasonable amount of time. So it's gonna be a figure out the secret type of question. You're the wrong code, actually. So we kill you. I'm thinking it's a sleep on it angle. Yeah, I'm gonna try to not spoil myself and sleep on this question if I don't get it right now, and then I'll think about it during the day. If I don't get it, do I come back to it or maybe just like look up a solution and code loaded up. I guess I'll see how I'm feeling. But what could the clever solution be? If the solution is actually like doing some sort of wicked gradient descent, I'm going to be very, very surprised. I mean, I think the problem could be solved that way, but also not expected to be the intended solution. Cause like, yeah, it doesn't, I mean, this point doesn't exactly. Maybe let me get my facts straight. Because I think it does actually no, what are we looping over? Oh, wait, it doesn't actually. I'm looking for a 1411. Oh, no, this is me experimenting. Oh no, it doesn't minimize this metric. But wouldn't that be logical? It's the furthest point, or maybe that's not true. I guess it really doesn't matter. All that matters is the closest sensors to the point, because who cares what's going on in the outside world? So from a given each sensor beacon pair draws a diamond on the map where things can't exist. How do you pluck out the point in the middle of these diamonds? it is dark. Music. Nice. How do we pluck out the point in the middle of all the diamonds? I don't think the structure of the diamonds themselves gives us any help to finding that specific spot. I think we have to do something. Right, because this point here is just maximizing the distance between all the closest things, and it's like sphere of influence, right? Like these ones will have spheres of... Do you arbitrarily pick the... Is it like a clustering problem? Like here? Like why couldn't that spot be here? Well, because this is exerting way too much influence. It's just shading in everything here. No, I mean... I don't think that's a good way to think about the problem. With any luck, that'll give me an answer in a few years. We can come back in a few years and click submit. Yeah, I apologize if there's... I don't think anyone here is actively chatting messaging, but I've closed it because I do want to try to do this spoiler free, at least for one night of brain sleeping and thinking about the problem. But I should really call it. I do have to wake up tomorrow for work. I don't think it matters that there is a beacon there. You can just as easily think of the beacon as not being there because it'll be less than or equal to become spots that it can't fill. So I think it's acceptable to ignore the beacons. I think it's just the Manhattan distance between a point and its beacon is the important metric. What happened? Why did we scroll down? Didn't do anything. Like, I don't think there's a cheap way to say, hey, skip over points that seem like they're already too close to something without actually... like, is there some analysis you can do on these actual points themselves to guess where the hole might be? Like, I don't think you could have figured that out through here. Is it gonna be something completely absurd, like we sort these points, and then you can do an independent sweep over which locations are not very common. I mean, we'd be at 14, 11, but we actually had something along there. Yeah, like 11 was here. I don't think so. I don't think it's a good way to do it. I mean, sorry. Obviously there's a good way to do it. I don't think I'm gonna come up with the good way to do it. An exhilarating stream of me staring at this diagram, trying to make sense of it. At least there's music. Oh, it'd be a shame if... Okay, at least there's music. Yeah, it's like... Who's on the edge of all these diamonds of influence? Oh! Maybe it's like draw the edges, search along the edges of the diamonds and all the neighboring points. Because we know it has to lie somewhere on the boundaries of at least one of... Yeah, it lies... It's the intersection of, like... It'll be plus or minus one of a boundary point on at least one of the... the boundary points on one of the things, and I think that is a much more reasonable thing to search. Okay, I think that's... We can try that out. We'll figure out how to translate that into code, and then try it out. I kind of want to just have that up as a picture. Day 15. Go. Alright. So the key, or I'm thinking the insight here is that it lies along the boundary points created by a few other sensors. So, in this case, it's like this J, its closest beacons are here, I believe. And so it's exerting this sort of sphere of influence, and this is like a plus minus on top of that. So we just try to generate all the inside or outward edges of plus or minus on the boundary condition of a beacon, and then do the check on that instead of whether it's a possibility. So hold on. Why you predict so much? So that's the only possibility. We come up with a generator, or we. Okay, let's just figure out if it's realistic to generate the set of all points along the boundary of the point. How do we do that programmatically? We go all the way out, and then we just draw a diamond. And then we're generating everything on that outer edge? Sure. So this is our starting point. We're gonna walk it. Okay. P is going to be equal to, or we're gonna go over to the left by delta S amounts, and then, cause like if we go over 1 because our distance is 1. Okay. This is an important number. And this is gonna be in range delta. We walk up northeast, I guess. And then we do the same thing, but we're walking southeast. And then we're walking southwest. And then we're walking northwest. No, stop. How reasonable are we? We're going up, we're going up. Oh, this is so hard to think about. so we start at 218. We do want to... Okay, we end at 218. We're going up. Ask where our beacon is. So the Manhattan distance there is... Sure, I'll just assume that's correct. But 218... We don't want to end up at 228. Oh, I mean, I guess we draw it like this. G is equal to... This is very helpful. Yeah, it's very helpful. We weren't offset enough. Why is that? Shouldn't... Like... Oh. Oh my god. Okay, stupid. Yeah, so... This is the outer edge of this, which overlaps with the beacon, and so any of the positions is like plus minuses on these, right? So I think this looks good, and then we do something like for G and Gen, and then for P in Gen dot neighbors, and then G dot neighbors. Why would we be running into a situation where we just don't have a delta value for S? Minus 518. How come you think there's a sensor at minus 518? Huh? Oh, I'm probably... I see. I have to make a new point, I guess, of s dot x minus d s dot y, like that. Probably like overwriting it, right? Okay. And then that's pretty reasonable. And then if not, if 0 is less than p dot x is less than what is it? We want the search space is tm. Like that. cool. So that should work, I guess. The real question is this fast enough? So the answer would be p dot x times 1, 2, 3, 4, 5, 6 plus p dot y. And now we change the restriction on the search space and we just run it. Oh, we run it without doing this stuff. And it's still kind of slow, I feel. But shouldn't this search space be a lot more reasonable? I mean, I guess we can narrow it even further by not adding things that are out of range here too. Oh. Oh, we did it. Ooh, okay, wow. That was a doozy of a problem. Let's take a quick peek at... You know, I am surprised that people were able to come up with this. I'm happy that I ended up being able to do it. We're running pretty late. So I do want to, but I do think it's worth it to go over the problem real quick. I'm not even gonna bother going into real time. I don't have chat open or anything, but this is our answer, right? Okay, so let's just remove all of this stuff that we don't need. We'll just clean this up a little bit and then talk through how to solve it. We don't need any of you. I mean, I guess we can use parsnips. We'll need you. We don't need any of you. Just clean up all of this stuff that we don't need. And try to come up with something good that's reasonable. I don't think we need to know what the min and the max are anymore. We don't even know what this is either. This becomes so much cleaner. Okay, we'll say sensor X, sensor Y, beacon X, beacon Y. So the first part of the problem is obviously parsing the input. Pretty straightforward. We can just use something to pull out the numbers, and we know that it's the first number is going to be the sensor X, second is going to be the sensor Y, so on and so forth. We don't need to keep track of the board, so we will draw it. We actually don't even care about where the beacons are either. All we really need to keep track of is two different things, where the sensors are, and I'll call the, what do we call this? We'll call this dists. So this is how far to the closest beacon for any given sensor. So that's all we really care about. We'll append the sensor location and then assign dists of the sensor to be the Manhattan distance between the sensor and the beacon. And of course the Manhattan distance is just going to be, or the taxi cab distance I guess, is absolute value of, 1 minus this on one dimension plus the absolute value of this minus this on another dimension. My points class helps make that a little handier. And because, so for this example, right, we have a sensor here and a beacon here, and the Manhattan distance is 1, 2, 3, 4, 5, 6, 7, 8, 9. This beacon is 9 away from this sensor, and so because the input tells us that this beacon is the closest to this sensor, no other beacons can be within 9 of this sensor, like going up, going down, or any permutations of that. So armed with that knowledge, I guess, we can start to answer question part 1, which is pick an arbitrary row. How many positions in that row cannot contain a beacon? In other words, if we say, for example, pick row 7, we look at a spot, we ask, can it contain a beacon? Or can it not contain a beacon? Well, how do we know if it cannot contain a beacon? Well, we can do exactly what we described here, where we look at every sensor, how far it is from a given beacon. And if the point is closer or the same distance to that sensor as its closest beacon, it disqualifies it as being a valid possibility, right? For the rule that we discussed before. So let's just try to encode that into code. I don't know if we need this yet. So part 1 is asking our starting Y location, just for doing testing, should be along row 10. And I guess we do want to keep track of the minimum X and Y for at least for part 1, so that we know that the possible search space. What's there a better way of doing it? No, that's probably a good way to do it. So let's keep track of minimum X, and we'll set it to a really big number at first. And max X, and we'll set it to a really small number. And then we'll say min of X. I guess all we really care about are the sensor locations. So min X is going to be the min of min X and the sensor X. And max X is going to be the max of max X and the sensor's X position. So now let's answer part 1. So we'll fix our Y position and just go across the row and check every point in that row. So for X in, and what values we want to check? Well, we want to check starting from minimum X, and just for good measure, let's oh, that's why I had the maximum distance, because starting at a given sensor, we want to know how far in this direction we should be checking. We know that this can extend at most as far as the closest, as far as the furthest sensor out to the left, and then as far as it can see. or just to make things easier because it's a similar order of magnitude as far as any sensor can see. So we'll say that the max dist is going to be the maximum of dist.values, and we'll subtract max dist from to kind of start our search space, and -1 just for good measure. I don't know if it's necessary. And we'll do the same sort of thing. Maybe we'll just call this MD now. We'll use better names. The max distance from any given sensor to its beacon, and then +2. So this will be our search space. This might be wrong, but I'll have to check it later. We can define our XY point just to make arithmetic better, and then we'll do exactly what we described before. So we'll go through every sensor for S in sensors. We'll ask how far is this point from that sensor. So the distance is going to be the Manhattan distance from this point to the sensor, and then we ask, is that less than or equal to, so is this distance less than or equal to the distance from that sensor to its closest beacon that it knows about? If we are in this range, then we know that this location is blocked. So if this is true, then we are going to mark that spot as taken, basically. So we'll increase the count. We found a location where a beacon cannot be, and then we can break because we don't have to check any of the other sensors. At the end of this, if we did this correctly, and we grab the sample input again, we get sys was not defined because, of course it isn't, I removed the import. I just don't want to have the code from part 2 executing. So we get 27 here, and why is that? Well, I think it's because in here, there's a spot where there is actually a beacon. So maybe it actually is important to keep track for part 1 of where the beacons are. That's a little tricky. Beacons.append B. And we only increment it if a beacon isn't already there, and I guess if a sensor isn't already there. So if B not in, or if P, this given point that we're checking, not in beacons, then we will increment. I mean, I guess just for good measure, we could also say that we could check that for the sets too. I mean, for the sensors too, but this is probably sufficient. This is, I need to clear my terminal. So yeah, now we're getting the answer of 26 because we are not double counting like on top of where an existing beacon actually is. And then just because we don't need to keep track of ordering anymore, and we are iterating through things, these are very small lists. They're only order, what, like 20, a couple dozen elements, so it honestly doesn't matter, but I guess it's still a good practice to get into. So again, we are taking every point, we're figuring out the boundaries along the x. I guess we are fixing our y, yeah, and we're figuring out where we should start and end the search on the x-axis, and then just doing a check. We look at a point, we look at every sensor, and if for any sensor this point is closer to it or equal to its Manhattan distance from it to its closest beacon, we know a beacon cannot be there, and so we increment that count. So that's the answer to part 1. So part 2 now is a little bit trickier, where it's asking us to find a specific spot where there cannot be, where there's like a beacon hiding, basically, amongst all of these diamonds that these sensor beacon pairs are creating. And so for this example here, there can be a beacon hiding at 1411. So 1411, I guess, on this map is here. All the other sensor beacon pairs create diamonds that will like block off all of this space, but this spot will stay empty. It won't be diamonded. So unfortunately, I forgot to turn the music off. Let me just turn it down. Okay. This is what happens when you want to go to sleep. Because the search space in part 2, part 1 is very small, right? These numbers are not very big. We can just search every possible value. But for part 2, on the real input, these numbers are massive. It's on the order of magnitude of 4 million. And if you wanted to search a 4 million by 4 million grid, you're not going to do that in any reasonable amount of time. So you can't do it by simulation. So you have to come up with a trick to reduce the search space. It took me a couple hours to get to that realization, but the trick is that remember that 1411 is this spot right here. And this spot is special because it's going to be surrounded in a sea of diamonds that basically say the diamonds represent the beacon cannot be here, and this is going to be kind of squished in the middle of a bunch of these diamonds. What we do know about the diamonds is we can easily compute the perimeter of them. And we know that the point here, because it's sandwiched between a bunch of diamonds, is adjacent to the perimeters of at least some of the diamonds, right? I guess it's easier to see if I had that old graphic up of all the grids drawn in, but you can imagine this sensor is closest to this beacon, so it's going to draw a diamond like here, which blocks off this space. This sensor is closest is here, so it's going to draw a pretty sizable diamond that's going to block off a bunch of space here. But regardless, this necessarily must touch the perimeter of a bunch of other diamonds. And so rather than search the entire n by n grid, we just have to search spots next to perimeters of diamonds. And that's what we're doing here. So in order to solve part 2, we loop through all the sensors and then do some logic to add all of the perimeter points to basically a list. So the logic for me doing this, I guess, is we start at where the sensor is, we figure out how far it is from its closest beacon, and then we subtract that from its x value. So we go out to here, basically. And then, for the distance of the perimeter, we walk diagonally, so add this to our list, add this to our list. We're going diagonally, walking up, like do. We get to the top, now we're going to walk diagonally down, do. We're going to walk diagonally down this way, and then we're going to go back up and finish drawing the perimeter. And we add this to our list of, I guess we'll rename things. So we can say this is perimeters. These are all points on possible perimeters. And then I'm going to, do I remember how to do things in Vim? Do I have to do a percent? Gen, change it to perimeters. Excellent. So, and to reduce the search space even more, we know that because this input goes like into the negatives quite a bit, that's like a lot to search through. The question tells us that we only have to search through values between 0 and 4 million. So, I just made this the cap. We can call this like max beacon, I guess. We do this max beacon. I want to do that again, like that. And so this gives us a set of all perimeter points on these diamonds that are basically drawn, which is great. And now all we have to do is search all the points next to these perimeter points. So for perimeter point in perimeters, we generate all possible neighbors of that perimeter point in the cardinal directions. And this is now called max beacon. I guess we don't need to do the check here because we're checking it after, I guess. I mean, we're checking it here. It doesn't really improve anything if we do that, if we make sure we're in this range again. And then we do a similar thing that we did in part 1, but kind of the opposite. We ask for everything in the sensor, we figure out the distance from that point to the sensor. If it's smaller than total plus or equal to 1, we don't need to do this. If that point's distance is smaller than or equal to the and this is called dists now, the distance to the closest beacon, we're in one of these cannot zones, and so obviously that's not the that's not our special location here that isn't covered, so we break out of this loop. Otherwise, if we get all the way through every sensor and that point is still valid, we haven't broken out, then we found the answer. So we can just submit the answer. So the tuning frequency is going to be equal to that point's x value times with this number again, magic constant, max beacon, 4, 1, 2, 3, 1, 2, 3, plus its y value. And we can just print part 2, the answer is the tuning frequency. And then we can just exit out. I'll just import this here. So if I didn't mess up renaming things, d equals deltas. Delta's not defined. We call this dists. If we run this, part 1 is a little wrong here. Something happened in the refactoring, I guess. We're overshooting the number by a lot, actually. And part 2 is taking a while to complete. I think I tapped out. I wasn't exactly sure how long it took part 2 to compute. Oh, okay. Part 2, we got the answer back. It took a while to look through all those points. Like, it's not fast by any means, and this is running in PyPy, so it's even more efficient. But we did get an answer in an okay amount of time, which is nice. But the question is, why is the answer for part 1 incorrect? Oh, it's because for the sample you're supposed to use y equals 10 for the row, but for the real deal we want to use 1, 2, 3, 1, 2, 3, 4, like that. Just because obviously like using this row doesn't make sense for such a small sample input at the start. So fingers crossed, yes, we get the answer. That was the answer for part 1. And for part 2, we already saw it. It takes a while to run. It has to check through a lot of points still. Like, it doesn't look like it, but these diamonds are massive, so there's a lot of different points to search through. But we still get the answer. So yeah, that was a very exhausting day of Advent of code, but we're still solving every problem in one sitting, which feels good. I'd be very curious if there is actually a more efficient or clever way of solving this problem. Maybe by isolating the different dimensions or coming up with some metric for guessing where it is, but I'm pretty pleased with coming up with this guess of looking up the perimeters of diamonds. Maybe it should have been obvious to me earlier on, but I was chasing a few rabbit holes that were not very fruitful. Of course, we can just clean up some more of these imports. We just want these directions, and we're also going to need to import file input like so. We don't need these anymore. For line in file input.input, we can do the same sort of stuff here. And then now we can execute it, day15.py, we pass in the input, and we're reading the input fine. We know this works. Cool. So that was day 15. It really was a doozy. I wonder how many people have actually solved the problem. Very few. Wow. Interesting ratio here. Almost exactly people got through part 1 and people who finished both stars. Obviously this will level out as the days go on and people start to trickle in and do these problems, but yeah, that was today's Day of Advent of Code. I am going to log off and get some rest, but if you stuck around, thank you for watching.